Welcome to week 4. We'll be talking about electrostatics more this week. So last week we talked about Gauss's law conceptually. This week we're going to do some calculations with Gauss's law. And it sounds like from the comments that for those of you who teach APC, this may be review. But let me know how far you go with Gauss's law in APC. Okay, so let's remind ourselves what Gauss's law is. So Gauss's law tells us that the electric flux through a closed surface is proportional to the charge enclosed within that surface. One important thing you need to remember, and it's one of the more confusing parts about Gauss's law, is that this surface is an imaginary surface. You may have a sphere that has a charge density inside of it, but to find the charge density inside of that sphere, you think of an imaginary sphere inside of it. And to find the charge density far away from that sphere, you think of an imaginary sphere that's much larger than the sphere that actually contains the charge. So we'll look at this with some examples. But before we go any further, we haven't really looked at surface integrals yet. A couple weeks ago we did the volume integrals we needed to do to find the charge enclosed. And last week we talked about surface integrals and how they're basically electric flux is a surface integral. But let's look at how we calculate the surface integrals that we need a little more exactly. Now we're not going to be doing the messiest of surface integrals. In general, you have to do a dot product between the electric field and dA. Now this dot product can vary either because the electric field changes in magnitude over the surface or the direction of the electric field compared to the direction of the surface varies. So at one point the electric field is perpendicular to the surface, at another point the electric field is parallel to the surface, at another point it's somewhere in between. So in general, surface integrals can be pretty messy. However, the way we're going to do this for Gauss's law is we're going to define our surface so that our electric field is perpendicular to the surface and has the same magnitude at every point on the surface. This is going to let us pull electric field out of the integral. We're going to go through a couple examples of the surface integrals you need, but once you understand those, you won't really have to work them out from the beginning every time. Okay. I know when I say a bunch of these things, it gets a little too abstract, and I'm guessing you need to see some concrete examples to see what I'm talking about. So let's look at some of the different geometrical situations we can find ourselves in. So let's first look at a surface charge. Okay, so let's say we have a surface of positive charge. It's an infinitely sized sheet. It's infinitely long, it's infinitely wide. Now it needs to be infinitely long or approximated as infinitely long in order to be able to make the approximations we make for Gauss's law. So to understand what that means, let's look at the Gaussian surface we're going to define. Because a sheet is basically rectangular, we're going to make a box. Okay, so my Gaussian surface is this box I've drawn here. So half the box is above the surface of charge and half the box is below the surface of charge. Our Gaussian surface does not need to be infinitely long. You might think that us getting to define how wide it is and how long it is and how tall it is would cause problems, but you'll see by the end of today's video that that'll all cancel out and everything will be okay. So let's look at this. So if you have an infinitely long sheet of positive charge, just take a minute and think about what that field's going to look like. We thought about this a little bit last week. Okay, so we're thinking about the electric field is away from the charge. So you can kind of see that if this sheet had edges, the electric field would start curving near the edges, right? It would start pointing out. And that would cause us problems because then the angle between the electric field and dA would change. But we need it to stay the same. So you can use Gauss's law in very specific cases. We'll talk about how you can calculate electric fields when we don't have nice symmetry, but we're just going to stick to nice geometries for now. Okay, let's look at another common example. Our next example is going to be a line of charge. Alright, so if we have a line of charge, let's say it's positive charge, then we think about our electric field, and we think our electric field is going to be pointing away from the charge in kind of a radial manner. Like if you were looking at this head on, if this was the front, and you were looking head on down your wire of charge, then your electric field would look something like this. But if we're looking at it from the side, our electric field looks something like this. So if we want to keep our electric field constant on the surface and always perpendicular to the surface, we need a cylinder. So this is our Gaussian surface. We get to define how tall the cylinder is, how long it is. We get to define its radius. That's really okay. And again, this line of charge needs to be infinitely long, because otherwise when you start getting to the edge of the wire, you're going to start getting your electric field going out to the sides, and then our electric field won't be perpendicular to the surface anymore. So that'll cause us problems. So Gauss's law isn't the best way to solve that particular problem. Okay, let's look at one more example, a spherical symmetry one. Alright, so if we're looking at a point charge, we can think about its electric field is going outwards everywhere. And it decreases with distance, but it's still spherically symmetric. So our surface for this one is going to be a sphere. And again, it's an imaginary sphere, so the radius can vary. So now that we've changed our situation so that we're setting so that the electric field is always perpendicular to dA, well, we don't really need to do a full surface integral every time. We can actually pull the electric field out, and then we have an integral just over dA. We're going to see that when you just integrate over dA, you get the surface area, but I want you to see that for yourself, since we haven't really talked about surface integrals before. So this is how we're going to be able to solve for the electric field, because we can pull it out of this integral. Being able to do that is really important. Let's go ahead and do an example where we do this calculation. Okay, so here we're going back to the situation where we have a surface of charge. So we have our box, and I've enlarged my box over here. And I've defined its dimensions. So it's h tall, L long, and W wide. And remember, we're doing advanced physics now. It looks like alphabet soup. Okay, so we want to think about what flux we need to calculate in this situation. So we know that our electric field on the top half is going up, on the bottom half is going down. So through the top half of the box, the flux is positive. Through the bottom of the box, the flux is also positive, right? Because dA for the top of the box is going to point up, dA for the bottom of the box goes down. So in both of those cases, the electric field and dA are in the same direction. But for the sides of the box, the flux is 0 because the electric field is parallel to the surface, or perpendicular to dA. Okay, so we need to calculate flux for the top and the bottom. And you would really expect the flux through the top to be the same as the flux through the bottom. The reason being that there's no reason that the electric field should be different going up than going down. Okay, so we do need to make sure we define our coordinate system. So I'm going to define x, y, z this way, and I'll put the origin on the back corner of the box. Alright, so I've gone ahead and drawn our cube on the XYZ coordinate axes here. Let me go ahead and put dA on here. So remember, dA always needs to point outwards. So how do we calculate a surface integral? So when you do a surface integral, you're integrating over two of your variables. So for the top half of the box, z is a constant, and x and y vary over the top of the box. So you're actually doing an integral over x and y. Now x goes from 0 to w, and y goes from 0 to L. For the top of the box, z equals h. For the bottom of the box, z equals 0. So doing an integral like this is like doing the volume integrals we did a couple of weeks ago, except now there's two variables, and it's time I gave you something to do. So what I'm going to have you do is actually calculate this integral right here. I'll recopy that on the next page. Okay, so go ahead and calculate this integral, where x runs from 0 to w and y goes from 0 to L. Alright, I'll go ahead and work that out. So we split it into two separate integrals. There's no reason we can't. The integral of dx is just x. The integral of dy is just y. Alright, so that's our dA for the top half of the box. It's actually the exact same integral for the bottom of the box because z is still a constant and x and y are still what varies. So this is dA for the top and the bottom. And you should always stop and think, what sign should my flux be? Well, for the top and the bottom, the electric field and dA are in the same direction. The arrows are pointing out of the box. So in either case, what you get is positive flux. So if you look at the flux for the top of the box, it's E times the integral of dA. So it's ELW. Same for the bottom. And for the sides, the flux is 0. Because again, the vectors are parallel to the surface. So our total flux is ELW. Now I'm sure you noticed that LW is just the area of the rectangle. And that is true. For all the cases we're going to do, we're going to end up with area. I just want to make sure you see where that comes from with surface integrals. But the simplifications we have to do to make Gauss's law work means that we don't have to do more complicated surface integrals. Oops. Sorry, the total flux is 2 times ELW. Okay, let's do another example. Alright, let's go back and look at the situation where we had a line of charge. So our surface is a cylinder. So the top and bottom of the cylinders have dAs going outwards. And then the dA from the side of the cylinder goes in the S hat direction. Remember, that's radially outward for the cylinder. We're going to define our cylinder to be h tall or h long, and we'll define its radius to be capital R. I'm defining our coordinate system. So that z is going to the right, y is going down, and x is coming out of the screen. So we have 3 surfaces we have to think about the flux for. And another thing I want to point out when we're thinking about how we define our various surfaces and how we define dA. So when we did dA in rectangular coordinates, previously we had dA was dx, dy because x and y were what varies. Now we're in cylindrical coordinates. As you may guess, based on our previous experience with cylindrical coordinates, this means things get a little bit more complicated. So instead of dx, we have ds. Instead of dy, we have s d phi. Part of the way you can see that we need that s there is to see that the units need to work out, because d phi doesn't have units of length. dz stays dz though, no change there. So if you had a surface where s varied and z varied, then you'd write ds dz, or if you had a surface where phi and z varied, you'd have s d phi dz. So that's something we have to keep in mind when we're working in cylindrical coordinates. So on the flat surfaces of the cylinder, the top and the bottom, or the left and right sides as it's drawn right now, on those surfaces, z is what's constant and s and phi are what varies. So dA is s d phi ds. So this is where z equals 0 and z equals h. If we're looking at the curved surface of the cylinder, well, on the curved surface, phi and z are what varies. S is r on that surface. That's basically what defines that surface. The curved surface of the cylinder is where s equals r. So we need to use phi and z because it's rotating around and we're moving along this way. So we have S d phi dz. Let me know if that makes sense. Then the next thing I want you to think about is what is the flux through these different surfaces. So if we look at our electric field, and when I say that, I mean in a very vague way. I mean, what is the sign, or is it zero? So for an infinitely long line of positive charge, the electric flux would be positive because the arrows for the curved surface are all coming out. But for the ends of the cylinder, there the field lines are parallel to the surface, so the flux there is zero. So our electric flux for the flat surfaces is zero, and our electric flux for the curved surface is positive. So the only one we need to do any calculations for are the curved surface. Now I showed you how to set up this integral for rectangular coordinates. I'm going to ask you to do this yourself for cylindrical coordinates. So what I want you to do is write out in cylindrical coordinates for the curved surface of the cylinder, what is this integral? So what do you need? ds, d phi, dz. What are the bounds of the integral? What do the variables range between when you do this? So go ahead and try out setting up this integral. All right, so what do we need to do? Well, on the curved surface, remember, this is where s is a constant, so s equals r. So dA, we already found on the previous page for the curved surface is s d phi dz. So phi is our inner integral. Phi runs from 0 to 2 pi. That's all the way around the circle. Z runs from 0 to h, the full length of the cylinder. And you can define the 0 wherever you want. It won't affect your result. Okay, now I want you to calculate this integral. Alright, so pause the video and try that out for yourself. Okay, so if we pull this out, we're going to separate this out into 3 different parts. Okay, so s is a constant when it comes to phi and z, so I pull the s out. Then I have an integral over z and an integral over phi. Well, I know that s is r on this surface. Then we integrate dz and get z. We integrate d phi and get phi. Alright, well again, this is just the area of the surface of a cylinder. The circumference times the height. You probably already knew that, but I really just want you to see where that comes from. Let's do one final example of doing this in spherical coordinates, and then we can go back to using this with Gauss's law. Okay, so we have our point charge. We know our electric field's pointing out. Well, because I do this for a positive point charge. Our Gaussian surface is a sphere of radius capital R. So, in spherical coordinates, again, when we're thinking about what dA is, we need to make some adjustments. So instead of dx, dy, dz, what do we end up with? Well, we have dr, we have r d theta, and we have r sine theta d phi. So if you have a surface where if you have a surface where phi is constant but r and theta vary, then you'd have r dr d theta. If you have a surface where theta and phi vary and r are constant, then you'd have r squared sine theta d phi. So you have extra bits in here. So for the surface of this sphere we're looking at over here, dA is in the r hat direction. On the surface, the radius r is what's constant. So I have some questions for you to think about on your own. I'm going to let you do a little more and more on your own as we go. So here are your questions. So I want you to figure out what dA is on the surface of the sphere. So remember, that's where the radius is constant. It's defined by little r equals capital R. I want you to tell me whether the flux through that surface will be positive, negative, or zero. I want you to set up the integral dA, so you already will have come up with what dA is, and then put the bounds on the integral. And then finally, I want you to calculate that integral. So do as much as you can on your own, but if you want to watch my solutions to each step by step and then press play again as you go, that works too. Whatever is best for the pace you need to go at. We are getting to the point where problems get pretty long, so I can't just show you something and then give you 3 examples. It doesn't quite work out that way when the problems each take as long as they do. Okay, so go ahead and give this a go. Press play whenever you want to check in. Okay, so what is dA? Well, little r is what's fixed, so theta and phi are what vary over the surface of a sphere. So we need to put together those 2 pieces. So we have an r d theta and an r sine theta d phi. Let's clean that up just a little bit. So we get r squared sine theta d phi. This comes up so often in physics, you'll start to remember it. Okay, what's the flux? What is the flux through the surface? Well, the electric field vectors point out of the surface, so the flux is positive. Next step, let's set up our integral. So it's a surface integral, so we need 2 integrals. Our dA we already came up with in part 1. Okay, the bounds of theta are 0 to pi, and the bounds of phi are 0 to 2 pi. Now let's go ahead and calculate this integral. So we're going to separate this out into 3 parts. Okay, so r is a constant as far as phi and theta are concerned. We've separated out our phi part and our theta part. Well, we know that little r is capital R on the surface, so we have r squared. Integrating sine theta gives us minus cosine theta. This is something you should remember, although you can always write it on your cheat sheet. Okay, what does this give us? Okay, and you should know your unit circle. If you don't have to memorize it, but I hope you will at least remember parts of it. So cosine of pi is minus 1. So minus 1 is plus 1. Cosine of 0 is 1. So this is 1 plus 1 is 2. Look, it's the formula for a surface of a sphere. If you didn't know where that came from, now you do. Super fun! So then if you wanted to find the flux through that surface, you just take E and multiply it times 4 pi r squared. So these are the geometries we're normally going to be working in when we use Gauss's law. And you don't have to derive the formula for the surface of a sphere every time you do the problem, but I think it's important that you know where it comes from. So basically we're going to do the electric field and multiply it times the area through the surfaces that have non-zero flux. And you're always going to have to stop and think about what the sign of the flux should be. So if we simplify things, we can now say Gauss's law is the electric field times the area through the surfaces that have non-zero flux equals the charge enclosed divided by epsilon naught. And I'm getting the impression if you teach APC, you probably do this with your students already. But I hope even if you do already do it with your students, you have a little bit better understanding of where this comes from now. So when you do this, make sure for your EA that this is coming from every surface with non-zero flux, and you're watching the signs for what your flux is supposed to be. Alright, let's actually use Gauss's law to calculate the electric field now.